Welcome back. In this video, we'll discuss sections 8.3 and 8.4 on partial derivatives. I'll illustrate this concept using the project from this unit, which is called wind chill. And so we're going to be using this chart to determine the wind chill based on the temperature and the wind speed. So just to kind of get you acquainted with this chart, there are a couple of places where we have a wind chill of 0 degrees Fahrenheit. The first would be right here. This corresponds to a temperature of 15 degrees Fahrenheit and a wind speed of 15 miles per hour. And there's one other place, I see a 0 here. This corresponds to a temperature of 20 degrees Fahrenheit and a wind speed of 35 miles per hour. So you see this formula at the bottom of the chart for calculating the wind chill, whose units are degrees Fahrenheit, based on the temperature T and the wind speed V. So for now, we'll ignore this formula. A little bit later, you'll use that in the project. So let's do this. Let's estimate the rate of change of wind chill with respect to wind speed when T is -5 degrees Fahrenheit and V is 30 miles per hour. Because we're wanting the rate of change of wind chill with respect to wind speed, we're going to fix T, the temperature, at -5 degrees Fahrenheit and let V, the wind speed, vary. So you can think of this as being stuck in this column here corresponding to a temperature of -5 degrees Fahrenheit. So we're just going to be moving up or down from this wind chill of -33 degrees Fahrenheit. And you can see that from the chart here. I put a yellow box around this entry for the wind chill at a temperature of -5 degrees Fahrenheit and a wind speed of 30 miles per hour. So let's estimate this rate of change by calculating an average rate of change. That's why I've got change in W over change in V here. You have a couple of options. You could move up or down. I chose to move down, which corresponds to increasing the wind speed. So I'll take this entry here, -34 degrees Fahrenheit, subtract the -33 degrees Fahrenheit to get the change in W over a change in V. Well, this wind chill here, -34 degrees Fahrenheit, corresponds to a wind speed of 35 miles per hour. And then we subtract the 30 miles per hour to get -1 degree Fahrenheit over 5 miles per hour. And this reduces to -0.2 degrees Fahrenheit per mile per hour. So you can think of this as for every 1 mile per hour increase in the wind speed, the wind chill decreases by 0.2 degrees Fahrenheit. The rate of change we just estimated is called a partial derivative. We're holding one variable fixed, in this case t, and letting the other, v, vary. So we're going to use a special notation for the partial derivative. It's this funny looking d. I'll call it a script d. So this just denotes the partial derivative of w with respect to v. And I want it for a temperature of -5 degrees Fahrenheit and a wind speed of 30 miles per hour. So I'll use this notation to denote that. And we saw that this is roughly -0.2 degrees Fahrenheit per mile per hour. Next, let's estimate the rate of change of wind chill with respect to temperature when T is -5 degrees Fahrenheit and V is 30 miles per hour. So now we're going to be fixing V at 30 miles per hour and letting T vary. This time we're stuck in this row corresponding to a wind speed of 30 miles per hour, and we're moving left or right. So we'll do the average rate of change calculation, change in W over change in T. You have to decide, do you want to move to the left or to the right? I chose to move to the right. So this negative 39 degrees Fahrenheit minus negative 33 degrees Fahrenheit gives the change in W, and then the change in T. Well, as we move to the right, this corresponded to a temperature of negative 10 degrees Fahrenheit minus the negative 5 degrees Fahrenheit to give us negative 6 degrees Fahrenheit over negative 5 degrees Fahrenheit, which is 1.2 degrees Fahrenheit per degree Fahrenheit. Now the units seem a little awkward here, but what this says is for every 1 degree Fahrenheit increase in the temperature, the wind chill increases by 1.2 degrees Fahrenheit. And I think that should make sense. As the temperature increases, we would expect the wind chill to increase as well. Again, we've estimated a partial derivative here. This time, we're letting t vary, and we're holding v fixed. We'd write partial derivative of w with respect to t. At this point, negative 530 is approximately 1.2 degrees Fahrenheit per degree Fahrenheit. Here's an example. Let's consider a function of two variables, f of x, y. It happens to look like this, x times e to the y. We'll start by computing the partial derivatives, or you might say first order partial derivatives. Let's do the partial derivative with respect to x. There's a couple of ways of denoting this. One would be f sub x. Another would be partial derivative of f with respect to x. These mean the same thing. So what we're doing is we're treating the other variable y as a constant and letting x vary. So any y's we see in this expression for f we'll treat as a constant. In this case, if y is constant, e raised to a constant is also a constant. So we have x times a constant. We'll just take the derivative of x like normal, that's 1, and the constant multiple e to the y tags along. So f sub x is equal to e to the y. For the other partial derivative, I'll write f sub y, or partial derivative of f with respect to y. Here we're going to treat the other variable x as a constant and let y vary. So this time x is a constant, y varies. Well, we know the derivative of e is itself, so we end up with this constant multiple tagging along, x times e to the y. Now that we've found the two first order partial derivatives, f sub x and f sub y, we can take the partial derivatives of these to get second order partial derivatives, and there will be 4 of them. Let's start with f sub x x. This is the partial derivative with respect to x of f sub x that we just found, e to the y. Here we treat y as a constant and let x vary. Well, if y is constant, so is e to the y, and the derivative of a constant is 0. For f sub y, this is the partial derivative with respect to y of f sub y, which we just found to be x e to the y. Here we're treating x as a constant and letting y vary. So this constant multiple x will tag along. We take the derivative of e to the y, which is itself, and we end up with x e to the y. For f sub xy, this is called a mixed partial derivative. We start on the inside and work our way out. So we actually take the partial derivative with respect to y of f sub x. F sub x is e to the y. Here we're treating x as a constant. There are no x's, so we just take the derivative of e to the y like normal to get e to the y. And for f sub yx, we're taking the partial derivative with respect to x of f sub y, which is x e to the y. Here we treat y as a constant, let x vary. So now this e to the y is a constant multiple of x, whose derivative is 1, so we end up with e to the y. And it's not a coincidence here that the mixed partial derivatives, f sub xy and f sub yx, are equal. For most, if not all, of the functions we work with, the mixed partial derivatives will be equal, and this is a result known as the mixed partial derivative theorem. So that wraps up our discussion of partial derivatives. I'll see you next time.